Just press X. So yeah, my talk title is HCI and static analysis. But before I get into that, I'm going to tell you a little bit about me, even though apparently I don't need an introduction. I am the founder and CEO of Nodejitsu, and I am on the internet. If some of you have heard of that. Now in Europe, they have this thing called net neutrality, which we haven't learned about in America yet. And recently, I am literally a master of HCI. Literally, I'm using that term correctly. And it's kind of like cats reading about military strategy. But it really stands for human-computer interaction. And so there's a really long, drawn-out definition about this that Chemistry Cat can tell you about. But really what you need to know is that it's a term popularized in the 1980s. And there was something else that was popular in the 1980s, this guy. And if you know this guy, you know that he fights for the user. So really, HCI fights for the user. Well, sort of. And really, on the internet, it ends up kind of being like this. So HCI and static analysis, what does that mean? It means that you write long, drawn-out academic papers called Towards Decreasing Mean Decision Time in Open Source with some convoluted title that you made up because that looks good on your published papers. But really, it's about NPM. Because you might know that I do a lot of work with NPM, and I couldn't really talk about it without showing this clip.
Chester A. Arthur fall down.
That's right. Chester A. Arthur fall down. And what I mean by that is, of course, NPM falls down. So why is this thing that falls down worthy of HCI research? It's worthy of it because, as you can see on this graph, it's got that big up and to the right sort of spike. And so soon it will be the largest open source platform worldwide. Lots of users means a good research area, and so on. But how soon will it be the largest open source platform worldwide? So as of yesterday, NPM and Maven had this many packages. So we're close. And they had an average, so that's 323. And they had an average rate of change of this, which is a difference of about 102. So that means that roughly by Tuesday, it will be the largest open source platform in the world. So pause for mind explosion. So please, tell me about your research study. So really, we conducted a research study on a small group of 8 experts who maintain lots and lots of open source code. The names have been changed to protect the innocent. And what we learned was that the most effective methods were used most infrequently. And that sounds kind of strange. And we used, academic things like Likert scales, which, if you know what they are, seriously, why does this need a name? So a Likert scale, if you've never seen one before, is something like this. So you can see sort of the effectiveness of things that you do. You open an issue, you send a tweet, and the question here was, how do you determine whether or not a change that you're making is breaking? Right? You have a library, it's popular, you have thousands and thousands of users. How do you figure out whether or not it's a breaking change? And how frequently do you do that? So you can see that people almost never write a blog post and never write an email. And those tend to be the most effective things in their perception. And these are, again, Likert scales. So now, a few minutes into my talk, I'm actually getting to the point, and I apologize for all of the academic hocus pocus at the beginning. But really, it's about Nyan Cat. I mean, really, it's about module authors and developers have questions about modules being developed, right? What code do I want to use? Why do I want to use it? Those sorts of things. And, HCI Tron must know, how do we do better? And it starts with something that you might have played with, but it's really that graphs rule everything around me. And if you've never messed around with graph theory, you should, because we're not talking about this type of graph. We're talking about this kind of graph. And all of these are different. If you are interested in graphs, I implore you to go learn more about them. But they're really used for everything, from transportation networks to information networks to molecular chemistry to wireless networks to Major League Baseball and even to lowly dependency management. So let's take a little bit of time to talk about dependency graphs. So, the G equals VE kind of graph. And I really don't like this visualization at all. It doesn't show you anything about the network itself. But thankfully, graphs do provide a basic structure for doing search algorithms, which can in turn be very useful. So to build our graph, we basically need to add a node for every package that we have. We then add a colored edge, and I'll talk about what a colored edge is in a second, to everything that has a dependency relationship. And they're colored by the type of dependencies, because if you use NPM, you know that there are dependencies and dev dependencies and peer dependencies and optional dependencies. The last two you really don't need to worry about. I'm sorry, I helped create peer dependencies. So to sort of give you the same example, this is exactly what this would represent. Very simple, package A has dependencies on B and C, and then has a single dev dependency on D. So now imagine this for 80,000 plus packages. Another mind explosion. Actually, it's not so bad. Hipster Cat will tell you. So dependency graphs are extremely useful for a number of applications, and we're going to consider two of them. The first one is codependencies, and this is where we get a little bit heady. So I apologize that you all haven't had your coffee yet, but we are going to talk about graph theory. So codependencies answer the question, people who depend on package A also depend on these other packages, and with what frequency, and how does that relationship work? And it all starts with a simple tuple of a package and its codependency exists through. And this is all really easy to calculate, thanks to CouchDB. Thanks, Couch. So to go back to our example, in this particular example, we would say that package B and C have a codependency relationship through A. And we'll get there. I'm seeing a lot of blank stares, but that's okay. So we can get all of this from a very simple CouchDB view. And if anybody knows how Couch works, they'll appreciate the sort of elegant simplicity of this. So we iterate through the dependencies twice, and then we go out and we emit that tuple with a single count. And we can then reduce that into some very interesting things. And I think the most popular module that I have is Winston, which made it a very easy canonical example. And if anybody's curious, that American depressed library makes no sense to me. If you want to go read some really weird code, go check that out. So get on with it. What are you doing? So for every module name, we generate a matrix. And that matrix visualizes the relationship, because if you know anything about graphs, you know that they can be represented by an adjacency matrix. This is very similar to that. We then rank the codependencies based on the number of times they appear. So going back to this example, oh, I hate it when Keynote does this, sorry. Going back to this example, we actually go out and sum these ones for all of the packages and then pick the top 10. It's a much easier way to think about it. Number of times that they appear. We then, for each of those codependencies in that set, go out and calculate that set again by removing that one package. So if we had the top 10, we would say go find the codependency relationship for the other 9 in that top 10. Everybody still with me? Too bad. And then we create a row C. And we end up with this very convoluted matrix, which actually is not very useful. The way that it becomes useful is that we have to weight these rows based on the expression of the codependency relationship in the overall pairwise grouping. So going back to a single example, we'll see that for, to go back to the top 5 here, so you'll see this is Winston again as the example. So the top 5 things that depend on Winston and this are things you would expect. Async, express, optimist, request, and underscore, right? People are depending on Winston and underscore, they're depending on Winston and request, they're depending on Winston and express, and so on. So then, for say one of those, we go out and calculate the total number of times that appears. So there are 240 packages that depend on Winston and async, there's 207 packages that depend on underscore and async, you get the idea. So of that 869 total, what percentage is that, right? 240 is roughly 27%, 207 is 23%. Then we go out and weight each one of those rows in the graph. So we would go weight each one of those rows based on that percentage number that we had. And I'm going to very quickly go back through this. So then we end up with this very, very fancy, nice-looking chord diagram, if you like data visualizations. And the chord diagram expects this type of matrix. So now you have this very dense data visualization that you're all probably scratching your head about, why is this useful? But it actually expresses a lot of information very quickly. And that information is the size of the arc is the degree of the codependency relationship with the parent module. So you can see that on the outside there are these big arcs. So underscore has a big arc, async has a big arc. That means that lots of people are depending on underscore and async with Winston. Then, if I could click a mouse, the size of the chord, which is the line between them, represents the degree of the codependency relationship between each pair. So for those of you who use Node, this is going to make tons of sense. There's a giant chord between underscore and async because almost every package out there depends on the underscore and async. Then lastly, there is a color. And the color itself represents the dominant pair between the modules. And this is where it starts to get really heady and interesting. So you can see that Express, almost everything is green, except for Redis. So basically, most of the time when people are going out and looking for modules and they're using Winston, they care about Express more than everything else, which actually makes sense because it's a very commonly used logging library. So I'm going to pause for a demo. And that didn't work the way that I wanted it to, but that's okay. So this is our same example from before, but there is, oh, no, this is Mongoose. So now we can sort of see what that matrix is and where it comes out to and all those sorts of fancy things. So you can see Commander is one of those sort of multi-purpose libraries, as is Colors. Notice that Colors is never dominant. In any of those particular examples, there is no dark blue chord, which means that it's kind of a utility library that's used all over the place. So, oh, and this is, of course, the dev dependency side of things, which is itself somewhat interesting, but less so because there are not that many people that respect that. So this is all open source. I mean, seriously, what else do people do? So you can find that, and that is, of course, on GitHub. And you can go and open issues, and I'll fix them, and maybe if we work together, we can go back to the future. I was just bored looking at the Octadex last night. I just couldn't help myself. But that's not all. That's not all. But before I continue, I have a brief, shameless plug. I will be brief, I promise. It's not all top hats and monocles. It's more like GitHub for production JavaScript. These are the types of questions that we ask, but I'm done. So the other piece of this, the static analysis piece, comes later. And it's kind of like, I can't really talk about this static analysis thing without talking about Richard Nixon. So for those of you who don't know, Richard Nixon was the 37th president of the United States of America. He was a pretty awful president. But Richard Nixon isn't really the point, although his head in the jar is pretty funny. What it's really about is this idea of a silent majority. He has this famous speech from the 70s where he basically coined this fear of a silent majority in America. And as a module author, you really have that same fear that there are a ton of users out there that are using your library and they don't talk about it. They just go off, and if they get stuck on a problem, they think they're dumb and they are just quiet. They don't open an issue. So how do you figure out what everyone's doing in an objective way that doesn't require any human interaction? And you do that using Esprima. And basically, if you've never used Esprima, it takes your code and transforms it into an abstract syntax tree, which you can then walk and start to find out very interesting properties of. And I promise I am getting to the point already. So using Esprima and a dependency graph, we are able to figure out what the hottest code paths are in a module. So you get somewhat of a not very interesting graph right now, but again, this is Winston, and there are some interesting side effects here again as the person who writes this module, which is that you can see that there is a log method there, and info, error, debug, warn, verbose are all helper methods that basically wrap that method. So to see log used directly as much as, say, a warning level is very interesting to me and tells me something about what people are doing. So it gives the author quick feedback instantly and avoids that risk of a silent majority. So again, this is all open source. Yep, just like before. And I'm actually pretty far ahead of time by about 3 minutes. So I'm done.